The aim of the present work was to characterize the cavitation erosion behavior of aluminum silicon 10 magnesium alloy produced by laser powder bed fusion, coated with a multilayer consisting of electroless nickel phosphorus and diamond-like carbon. For this purpose, aluminum silicon 10 magnesium plates were produced through laser powder bed fusion. Then, some of the samples were tumble finished and then coated with NIP. After, some of the samples were also coated with a DLC top coat. The conditions tested in the present work were the bare alloy, the NIP single layer coated samples, and the multilayer coated samples. Cavitation erosion tests were performed using an ultrasonic device for a total test duration of 8 hours with periodical interruptions, at which the samples were weighted and then the eroded surface morphology was examined. The main results are now shown. In this slide, the cumulative mass loss and the erosion rate as function of time are reported, allowing the determination of the characteristic stages of cavitation damage. First, the incubation stage, where the erosion rate is negligible, corresponding to the accumulation of plastic deformation preceding significant material loss. Then, the acceleration and maximum erosion rate stage, and finally, the deceleration and terminal stage. This table summarizes the main parameters obtained from cavitation tests. Aluminum silicon 10 magnesium alloy presents the immediate onset of material removal. For the NIP coated sample, the incubation time is comparable to the bare alloy. The large coating fragments detachment from the NIP coating resulted in higher mass loss and erosion rate compared to the bare alloy. For the multilayer sample, a two-stage incubation behavior was detected, where the first incubation period corresponds to the incubation time of the DLC coating, while the second is attributed to the substrate. The multilayer coated sample shows a longer incubation period and then a limited mass loss. Aluminum silicon 10 magnesium shows the typical cavitation erosion mechanism of metallic materials. The NIP sample presents pre-existing discontinuities before incubation and a large coating detachment at the incubation time. At the first incubation time, the DLC sample presents detachment of DLC in very small areas, starting mainly from the discontinuities or defects of the underlying NIP coating. It was also seen that after DLC detachment, the erosion proceeds as in the NIP sample, with cavitation erosion damage localized in region corresponding to NIP morphological discontinuities. The cross-section analysis at the end of the test shows surface-initiated cracking in the NIP sample that propagates through its thickness. To summarize, the multilayer system significantly improves the cavitation erosion of aluminum silicon 10 magnesium alloy thanks to the increase of the load-bearing capability of the NIP layer and the high hardness of the DLC top coat. The damage was found to origin from surface discontinuities and defects, suggesting that an improvement of the surface finishing may be of further benefit to the multilayer coating.